Hey everyone, and welcome back to Psych 3510. In this section, we are going to introduce a concept known as Z-score, which really piggybacks on the last section that you should have completed, which was on variability, where you calculated a standard deviation. And remember, standard deviations provide us with information about the spread of data around a mean. This is going to be important for our decision making as we use statistics in the future, because if you remember back to chi-square, we are convinced by extremity. Right? We are convinced by extreme results. Extreme results provide us with good, convincing evidence of something. And so if we have a measure of variability, like a standard deviation, we can start applying that knowledge to decision making about the world. We're gonna see that here for the example or the concept we're gonna use as an example called z-scores. So one way to think about this is, someone is claiming that they are tall, right? That's their claim. I'm a tall person. We want to evaluate whether we should believe their claim or not about being tall. So if we're going to judge whether or not someone is tall, we need to know the average height, but then we also need to know how much people vary around the mean, right? So if the average height is 5'10", and people are very, very close to the mean, then that allows us to make a decision about a particular individual who maybe is 6'2", right? We might judge them to be quite tall in that case, versus a situation where maybe the average height is 5'10", and people vary a lot around the mean. For whatever reason, I've got a whole bunch of 6'4", 6'6", 6'8" people, right? This variable just has lots of spread. And so because of that increased spread in the data, suddenly a height of 6'2" doesn't look as tall anymore, because there's lots of people out there in those extremes or away from the mean. And so what we want to do is build a way in which we can evaluate the relative extremity of any given person along a distribution. So that's what we're going to do with z-scores. They're going to allow us to evaluate the relative extremity of an individual when compared to a population or the distribution about which we have information. So we can think of z-scores as overlapping with what we call the normal probability distribution. This distribution is a theoretical distribution, meaning you're not going to actually collect data and find this like perfect smooth curve every time, right? If I collect 100 data points, the data points fluctuate. It's not going to be this perfect, beautiful curved distribution. But theoretically, right, on a long enough time scale with enough data points, all normal variables fall into this shape of a distribution. If I have, 10,000, 100,000, a million data points, all variables will start to look like this. So what does look like this mean? Look like this means that we have our mean, right? As we've discussed previously. Our mean is also the most frequent value, right? That's what this y-axis is in a probability distribution, just like with a frequency distribution. So if I fall right here on the distribution, it means I'm perfectly average, right? Half of people are above me and half of people are below me, right? If I fall on this vertical dotted line. As we move away from the mean in either direction, then scores become more extreme and they become less common, less likely, right? As we move sort of down the curve, the space under the curve is smaller, which tells us that there are fewer people out here in the curve. So if this is height, and let's just say average height is 5'10", then we could make judgments about the relative extremity of someone who's 6 foot, 6'2", 6'4", right? Where presumably as height increases, they are moving away from the mean to the right, and thus the scores are getting less and less common. And the same thing for below the mean, right? 5'10" to 5'8" to 5'6" to 5'4" becomes less and less and less common, and thus the curve reflects that. So all that this curve says, the only thing it says is that on average, under normal circumstances, with enough data, variables will have a distribution that looks like this, such that most people center around the mean, right? That describes the variable best, and most of the data is around the mean. Most people are close to average. As we move away from the mean in either direction, then the frequency or the probability of those scores becomes lower and lower and lower. There are fewer people out here in the tails of the curve and a lot of people here around the mean. So you can also think about this in terms of something like GPA. Right? So let's say the average GPA is 3.0. Lots of people are right around 3.0. Right? I've got a lot of people who are 2.9, 2.95, 3.0, 3.1. And then as I move away from that mean, as I get to 3.3, 3.5, 3.8, 4.0, I have fewer and fewer and fewer people with that GPA level. And so if we can place someone's score on this curve, that's what a z-score is going to do for us, spoiler alert. If we can place someone's score on this curve, we can start to make decisions about the proportion of people they are greater than or less than. And so that's really going to be useful for us in making decisions about extremity, right? Because if I said that I'm tall, but 40% of the population is taller than me, then I'm not very tall, right? That's a bad claim. It's a poor claim. If I claim that I'm tall, but only 2% of the population is taller than me, then suddenly I look very tall because most people are shorter than me and only a few people are taller than me. So fitting someone's individual score along this curve is going to allow us to make these relative judgments of their extremity. So, when we fit standard deviations to the normal curve, then some interesting properties arise. So because this distribution is standard, because standard deviations are standard, because it's normally distributed, then these probabilities sort of pop out of the curve, such that we can start making claims like 0 here represents the mean, right? That would be 0 standard deviations away from the mean. So between 0 and 1 standard deviation above the mean, you will find 34.1% of the population that would score within that bracket. Now remember, a standard deviation is the thing that we learned how to calculate from variability. It's a measurement of the standard amount of deviation around a mean in a data set. So again, this is making the assumption that I have a very large data set, lots of data on a normal or typical variable like height, like weight, like IQ, things of that nature, depression scores. And so if I have that standard deviation value, right, that the standard deviation of IQ is 15 points, or the standard deviation of depression scores is 3 points on whatever my measurement is, then I can fit those standard deviations to this curve, and it will tell me how extreme people are. So 1 standard deviation above the mean puts me right here. And now suddenly I can make this claim about what percentage of people are above me or below me, because these percentages that bracket our standard deviations are consistent across variables. That's what it means for a standard deviation to be standardized. That's the point, is that it doesn't matter if we're talking about height, it doesn't matter if we're talking about weight, it doesn't matter if we're talking about IQ, it doesn't matter if we're talking about depression or how those things are measured. If we meet the assumptions of this normal curve, these percentages will be the case. So the percentages here up top tell you the proportion of the population that can be found within either any of these standard deviation brackets. So 0, the mean, to 1 standard deviation below the mean, 2 standard deviations below the mean, 3, 4, and 1, 2, 3, 4 on the high end. Notice these probabilities decrease as we move away from the mean, just like we said previously, because as you get more extreme, there are fewer and fewer people out there in the curve, right? There's only a few people that are 6'10". They're not very common, right? They're way out here in the most extreme proportion of the distribution. Just like there's not a ton of people who are 4'3", right? That's a very uncommon height to have, just like 6'10" is uncommon. And so there's not many people out there in the curve. They exist, but as we move away from the mean, as we increase the number of standard deviations that an individual is from the mean, the less common those scores become. So let's imagine that this variable is male height. Let's sort of flesh this out. And let's say male height has an average of 70 inches, which is 5'10". And male height has a standard deviation of 4 inches. So what that means is I can take this measurement of 70 inches and I can place that as my mean. Then I can, in increments of 4 inches, I can add 4 inches to 70 to get 1 standard deviation above the mean. I can add 8 inches to 70 to get 2 standard deviations above the mean, right? And if a standard deviation is 4 inches, then 1 is 4 more inches than the mean, 2 is 8 more inches than the mean, 3 is 12 more inches than the mean, so on and so forth. And then I can do the same thing on the other side of the distribution. So subtract 4 inches from the mean, then subtract 8 inches from the mean, and 12 inches from the mean. So let's do that here really quickly. If our mean is 70, and our standard deviation is 4, then the sort of positive side of our curve looks like this, such that I can now make the claim that 34.1% of men are between 70 inches and 74 inches, which comes out to 5'10" to 6'2". Now I can make another claim, right, that only 13.6% of men are between 6'2" and 6'6". Only 2% of men are between 6'6" and 6'10", and only 0.1% of men are taller than 6'10". So we took our mean and we added 1 standard deviation, sort of per mark here, such that we can now describe in great detail the positive half of our height distribution for men. And if you gave me any man's height, I could fit him to this curve and find out how common or how rare his height is. So this tells us a height of 5'11" or 6 foot is above the mean, but it's pretty common, right? There's lots of people that are 5'11" or 6 foot, but there's not many people that are 6'8", 6'10". And so, of course, I can do that on the negative side of the curve, where I'm just subtracting 4 inches, because 4 inches is our standard deviation. Again, we would have derived this from actually having a data set and calculating the standard deviation of height. This does happen to actually be the real standard deviation of male height at the population level. So I'm actually not just making these numbers up. This is what the data actually look like from the medical literature. So our mean is still 70 inches, but then we can list and understand sort of the drop off in probability of height going down the negative side of the curve, where we're 1, 2, 3, and 4 standard deviations below the mean. So again, minus 4 inches from the mean, minus 8 inches from the mean, minus 12 inches from the mean, minus 16 inches from the mean. And again, people in those areas of the curve become more and more rare. It's very common to find someone who's 5'9". It is not very common to find someone who's a man who's 5'2". Okay, so we can start asking questions. Remember, the whole purpose here is to ask questions about extremity because we are convinced by extreme results. So now suddenly we can start answering questions about extremity. Is it more common for a man to be 6 feet tall and fall roughly here on the curve, or to be 6'6" or 5'2"? And of course, where these heights fall on the curve based on our mean of 70 with a standard deviation of 4 inches. So what we can already say is that it's quite common for a man to be 6 feet tall. It's quite uncommon for a man to be 6'6", and it's also quite uncommon for a man to be 5'2". We can also say something really interesting, that it is equally likely that someone be 6'6" as they are 5'2", because this is a symmetrical distribution. So at the level of the population, there are as many men who are 6'6" as there are men who are 5'2", because 6'6" is exactly 2 standard deviations above the mean. 5'2" is exactly 2 standard deviations below the mean. Like I said before, the curve is also going to tell us percentages of above or below any single or between any 2 spots on the curve. So, for example, 34.1% of men are between 5'10" and 6'2". And 15.8% of the population is shorter than 5'6". How would I do that? Well, I would find 5'6". If my mean is 5'10", my standard deviation is 4, then 5'6" is exactly 4 inches or 1 standard deviation below the mean. And if I wanted to know what percentage of men are shorter than 5'6", then I can simply add up these probabilities to get 15.8%. So 15.8% of men are shorter than 5'6". So again, suddenly you have this really great tool at your disposal for making decisions about the relative extremity of a score. Let's do a quick practice problem here. Just I want you to think about it. I'll sort of just walk through this with you. Don't worry about pausing or anything like that. Again, our average is 5'10". Our standard deviation is 4 inches. If I were to ask you what percentage of men are taller than 6'10", taller than 6'10", so the first thing we have to do is find where 6'10" falls on the distribution. That is 12 inches above the mean with a standard deviation of 4. That means that a man of 6'10" is 3 standard deviations above the mean. So he's right here. And if this is where that individual falls on the distribution, it means that only 0.1% of men are taller than 6'10". This relationship of the percentages and the curve holds true regardless of the variable which we collect data about. So this could be the number of words that you remembered. It could be how often you argue in a relationship. It could be the average size of chimpanzee troops in the wild, right? It doesn't matter what the variable is. This standardization of probability will always adhere for every variable, provided that you know the mean and you know the standard deviation of that variable. So this allows us to make really informed decisions about extremity because we can create multiple curves, or we can create a curve for essentially any variable that we can imagine collecting data on. So here's sort of just a blank curve that doesn't have like a variable fitted to it yet. And so you'll often see these marked with the 0, 1, 2, 3, and negative 1, 2, 3. When you see this curve start with a 0 in the middle, then what that means is that we have standard deviations along the x-axis. Now, if we fit variables to it, it might look like this. So let's say you're a primatologist who's studying chimpanzee social behavior. And so you measure the number of individuals in chimpanzee troops. You find that the average, the mean number of chimpanzees in a troop is 32. And you find that the standard deviation is 6. You have the data, you have a data set, you ran the stats, and this is what you found. A mean of 32. So we could fit that here. And so now standard deviation of 0 is the mean. And so for this variable chimpanzees in a troop, this 0 effectively becomes a value of 32 for that variable. It's 32 chimpanzees is the mean. 6 standard deviation, or 6 chimpanzees is the standard deviation. So we would then add 6 each time to sort of investigate the extremity of chimpanzee troops on the positive side, and then subtract 6 each time for our 3 standard deviations below the mean, such that now I can say that a chimpanzee troop that only has 14 individuals is a very small troop, and a chimpanzee troop that has 50 individuals is a very large group. A chimpanzee troop with 33 or 34 or 31 or 29 individuals is very common because it's close to the mean. So the same nature of this relationship applies even if I have a different variable. Let's say that I'm a social psychologist studying relationships, and I measure the number of fights that couples have in some given time frame. Let's say 6 months, right? How many fights do you have in 6 months? I collect a bunch of data on couples, and I find that the average couple fights 7 times over that time frame with a standard deviation of 2 fights. So I can fit my mean to the center point of this blank standardized curve, and then I add standard deviations going up 1, 2, 3 times, right? Standard deviation of 2. So 7 becomes 9 for 1 standard deviation above the mean. 9 becomes 11 for 2 standard deviations above the mean. And I do the same thing going down. I subtract standard deviations. So now I can say that, well, if a couple only fights once in 6 months, that's really good. They do not fight very often. But if a couple fights 13 times in 6 months, that's a lot. There's a problem there, right? They're fighting way more than the average couple does. Because now that I've fit my mean and standard deviation to this normal standardized curve, the sort of nature of this variable, fights in a relationship, the nature of that variable spread becomes very clear to me, and thus I can make judgments about extremity. So the point here is that this relationship holds even as our variables change and even as our values change, right? These numbers, the 32 here is the mean for chimpanzee troops. And so it's essentially analogous to our 7 fights in a relationship. The numbers mean very different things, right? Here, 32 means 32 chimpanzees. Here, 7 means 7 fights in a relationship. So we can swap out variables, and that will change out the actual values along the bottom of this curve. But the relationship of the curve, the nature of the curve, does not change based on the variable you're using. Our same thing, percentages still apply. So we can say that some percentage of chimpanzees or some percentage of troops have fewer than 20 members, just like some percentage of relationships have fewer than 3 fights. Okay, so I know that's a lot. It's again a little theoretical at this point. The key things to take away from this are that this curve is standardized and it doesn't change even as you change out the variable and the values. And what this curve is going to allow us to do is make decisions about individual extremity using what is called a z-score. So what we'll do in part 2 is pick up from this slide, and we're going to break down how to calculate a z-score, what goes into it, and then how we can use it in a functional way to make decisions about extremity. So thanks for watching. Let me know if you have any questions, and I will see you for part 2.